Hi, my name is Richard Hellinga. I'm the Chief Technical Officer at Turntide Technologies. I want to thank Charged EVs for holding this virtual conference, and I want to thank them for inviting us to come and speak. So Turntide Technologies is a company that was founded in 2013. We were founded as a software motor company, or software motor corporation, and we were founded around the benefits of switched reluctance motors could bring to the use of motors around the world. To date, we've raised over $100 million in funding, including from BMW Ventures. And to date, we've also focused on HVAC-R. HVAC-R is heating, ventilating, and air conditioning, and we're focused on the retrofit market. And the reason we focus on that market is because switched reluctance motors dramatically reduce the energy consumption for heating, ventilating, and air conditioning. We've got thousands of motors installed at hundreds of commercial sites, and our customers are seeing significant energy savings. What I want to talk to you about today is the switched reluctance motor and how we think it's going to impact electric vehicles in the years to come. If you take a look at the evolution of the electric motor, in the 1800s, we started with direct current motors. And then Nikola Tesla, combined with the fact that we decided to settle on alternating current versus direct current, really pushed forward the induction motor. And then in the 1980s, what we found was that if we applied electronics to these motors, we'd actually be able to make them variable speed and hence variable torque. In 1990, you started to see the emergence of the switched reluctance motor. This was a concept where we said, we don't actually need windings on the rotor, or we don't need magnets in the rotor. And in 2016, we patented the high rotor pole switched reluctance motor. And this was a motor, and you'll see later, where we actually have more poles on the rotor than on the stator. So we think this is the first significant change in motors over the last 80 years. And really, it was enabled by the cost reduction in power electronics, because switched reluctance motors require electronics to make them work, and also the software, both to control the current within the switched reluctance motor and the software to go and design these. So if you take a look at motor technology in electric vehicles, in the 1960s, there were electric vehicles, and they were generally brushed motors, very often simple series motors. And that went through until the emergence of why can't we have vehicles on the road that are actually electric based. The most famous example is EV1. That was an AC induction motor. And then Tesla with its Roadster, which was also an AC induction motor. And then PRIUS, who sort of demonstrated the fuel efficiency that you could achieve by using an optimized hybrid system. They used an interior permanent magnet motor, and recently, I'm sure you've read the news, that Tesla's also moved to an interior permanent magnet motor. We think that in the future, you will also see switched reluctance motors. And the rest of the presentation is to tell you why we think that is true. So the first reason we think that that's true is because switched reluctance motor technology is improving more rapidly than any other. It's really a relatively new technology where a lot of energy is being invested. And we think that that will pay off in more rapid increases in switched reluctance motor than in any other technology. The other reason we believe that it's going to grow in vehicle applications is because in labs, we've already shown that switched reluctance motors can exceed IPM performance in vehicles, and we'll spend a minute or two on that. And the other reason is that IPMs require rare earth materials, and if the motivation for electrifying our world is to reduce our environmental footprint, if one of the motivations is for that, then we think that ultimately that will also go back to reducing our environmental footprint in the materials that go into these technologies. And finally, we'll wrap up with listing some switched reluctance motor advantages that we think are just too compelling to ignore. So this is a slide which was published in a 2019 paper We've added a little bit to it, which shows essentially the major milestones in switch reluctance motors. And you can see it started in 1992, but between 2000 and 2015 is when you started seeing a lot of activity and a lot of advances. I just want to, you can read this on your own, but I wanted to point out that in 2010, that's the slide, the picture of the high rotor pole motor that was developed by PRIUS Desai, who is our chief motor designer. When he was at the Illinois Institute of Technology, this was the subject of his PhD thesis. And we've continued to take that motor and continue to develop it. So here's an example of why we think there's still room for rapid development and evolution in switch reluctance motors, while other kinds of motors are seeing diminishing returns. And another way to look at this is that we keep, at Turntide, we keep a pretty close eye on what's happening around the world. We have relationships with many of the leading research institutes. And around the world, we count 260 places where people are doing development and working on improving switch reluctance motors. And frankly, we think that if there are 260 locations around the world looking at this, that we're going to see dramatic improvements in switch reluctance motors. And then finally, if you just take a look at our own work, we've seen dramatic progress over the last 10 years. We've seen our own efficiencies improve to the mid 90%. We produce motors which go into industrial or commercial applications, and we've now achieved a 2 times power density versus the AC induction motors that we're replacing. And so what that means is that customers get for a given NEMA frame size, they get a much higher horsepower. And with our Q series motor, we've seen a dramatically reduced acoustic noise. So all of our own activities convince us that prior issues of noise and torque ripple, that we've done a pretty good job of mitigating those. And the other thing is that it's not only the motors that we produce, but how we design those motors that we think bodes well for the future. So we take a simulation-based approach, and we have a very significant program underway with ANSYS, where we do multi-physics design of these motors. And we have seen the impact of that on our motors in the past, and we expect that to accelerate in the future. So the second reason why we think that SRMs are going to have a role in vehicles in the future is some of the lab results that are coming out around the world. And this is a published paper coming out of Tokyo Institute of Technology. Professor CHIBA has done a lot of work on SRMs. And this is a summary of one of the papers that he published, in which he took the 3rd generation Toyota PRIUS motor, and he set about to make an SRM motor that would be equivalent or better. And the green, this is a summary of it, and the green box shows where the SRM motor was better than the than the IPM motor. So you can see that there was a lower current, which resulted in a higher maximum peak torque. It's a significantly higher power, and he set about to have the same envelope, and consequently of a higher torque density. The only area where it was worse was in the mass, and that's essentially because we're putting more copper into the motor. And of course, the big advantage is that there are no magnets in this thing. Now, if we dig a little deeper, this is the efficiency map of Professor Chiba's motor, and he highlights sort of the targets for this and what he actually achieved. I think one to look at is that he targeted a 60 kilowatt, and he actually achieved 100 kilowatt. The more interesting chart is if we compare that switch reluctance motor to the IPM that he used as his benchmark. And again, this is from his papers. And the way you read this chart is that the division between the green and the blue is where the IPM motor and the SRM motor have exactly the same efficiency. But as you go up into the green, the yellow, and the red, the SRM motor has a higher efficiency. And as you go into the blues and the blacks, the SRM motor has a lower efficiency. So what you can see is that overall, the efficiency is, this area here, the 0% is the same, but overall, the SRM motor is more efficient. And in fact, out near high speeds and low torques, it's dramatically more efficient. In fact, at high speeds, it's dramatically more efficient. Where it has lower efficiency is at low speeds and very high torques. And it's important to overlay this with your drive cycle. And typically in drive cycles, you don't spend a lot of time at very low speeds and very high torques. So we think this is a chart which shows the promise of SRM motors. And here's another way of looking at how do SRM motors compare out of a 2019 paper, which compares, for example, power to weight ratios. There's a number of ways that you can look at this. And again, this shows that SRM motors are certainly very good here. Now, again, I want to just highlight that we still think that SRMs are in their adolescence. We think that there's still room to move with SRM motors. So the third reason why we think SRMs will show up in vehicles is because of the rare earth materials. So here's some pricing over time about of some of the significant rare earths. But more important than just the pricing is the fact that of where these materials come from, and that they're subject to essentially all the trade unrest that might go on. So China's 6 state enterprises control 90% of the world's reserves. And as some examples of this, in 2010, China and Japan had a trade dispute, and one of the tools in that trade dispute was rare earths. And China, for a time, cut exports to Japan. In 2019, as part of the ongoing US-China trade unrest, China threatened to cut the supply of rare earths to the US. Now, they didn't end up doing that, but what you can see is that the rare earths are subject to, particularly rare earths are subject to the ongoing trade unrest. And because there's an asymmetry in that, it is a cause for concern. One other thing about rare earths is rare earths are not actually that rare in their natural occurrence, but it is very difficult to extract those rare earths, and it's very environmentally expensive to do that. So again, like I said at the beginning, if we are trying to reduce our footprint by electrification, then we also have to consider the impact of rare earths. Finally, the other reason why we think that SRM is going to have an increasing role in vehicles is some of the other advantages, which I haven't talked about. So an SRM motor is the simplest machine that you can build. It's cheaper to source and manufacture. It has windings, which can be done on bobbins, so they don't have, you don't have different potential windings touching each other. So it's very easy to make. They're very reliable because they have only, it's really down to the bearing life. The rotor is strictly made of silicon steel. There's nothing else in the rotor. You can have very high temperature operation and for higher peak powers because you don't have magnets that you need to be cautious of exceeding their temperature limitations. This is the next one's fairly significant. Any sort of permanent magnet motor has a back EMF, and very often in vehicles, you actually exceed, the maximum rotating speed actually exceeds, the back EMF exceeds the battery supply voltage. So you have to take great care about fault conditions at high speeds. And secondly, if you have, for example, a 2-motor vehicle and you decide that you want one of your motors to coast, then at high speeds, you actually need to put energy into that motor in order to counteract the back EMF or the magnets that are there. And you therefore consume energy to produce zero torque. So this is a pretty distinct disadvantage. So they're fault tolerant and they have safer failure modes. So they're fault tolerant because if you do have a failure in a phase, you can continue to run the motor on less phases. You will not produce the same torque, you will have increased ripple, but you can still run. And the safer failure modes are because if something goes wrong, you don't generate high voltages and you don't need to short circuit the currents that are there. So you can actually have a failure mode in which you coast. And that's very difficult to do with a permanent magnet motor. Finally, I'll do the last two in the reverse order. Because the end windings are very small, you can make very efficient use of space. And if you take a look at a motor, the distance from front to back, more of that motor will have the lamination stack in there. So more of the motor is torque producing, and therefore you can actually end up with pancake form factors. So those are the reasons why we think switch reluctance motors will play a role in vehicles in the future. At Turntide, we're not only saving customers energy today, but we're investing heavily into switch reluctance motors, and we're excited to see how that might turn out for vehicles in the future. Thanks again to Charged EVs, and I appreciate the chance to address you. Thanks.